Some solved problems for chapter 21. I've gone ahead and drawn it out already to save you the agony of watching me draw it. 3 charges in a line. Q3 is 5 nanocoulombs. Q1 we don't know the charge of, and Q2 is -3 nanocoulombs. And we know the location of Q1 and Q2, and we're told that the net force on Q3 is equal to 0. So if I draw the force from Q2, that's a negative charge, is going to attract this, is going to attract the positive charge, so that's going to be force 2. We know that force 1 is going to need to balance that out, so I'll draw the force due to charge 1, and that tells us immediately that Q1 must be positive. Now it's a simple matter of balancing out, or writing that force 1 must be equal to force 2 and use Coulomb's law, and so that's going to be K Q1 Q3 divided by the distance to 2, or the distance to 1 squared, and this is going to be the magnitude of the charges, because I already know that Q1 is going to be positive. Here we're going to have K Q2 Q3, again I'm using the magnitude here, divided by the distance to 2 squared, and we can see that my k's are going to cancel out. We can actually see that Q3 is going to cancel out, and I can write Q1 to simply be equal to Q2 divided by R2 squared multiplied by R1 squared. So that's going to be equal to 3 nanocoulombs multiplied by 2 centimeters squared divided by 4 centimeters. That's going to be, pull the squared out right there. We can see that the units of centimeters squares are going to cancel away, so I actually can get away with just leaving it in centimeters rather than converting it to meters. And I'm going to come up at the end of the day with 0.75, keeping the units of nanocoulombs. In 2145, we're taking a look at finding the electric field and then using the force is equal to charge times electric field. 2 charges, Q1 positive 2 nanocoulombs at the origin, Q2 -5 nanocoulombs at 0.8 meters. And we're asked to solve for the electric field in a couple of places. I'll just do the first one because the other two more or less just follow on. So we're looking at this point right here, 0.2 meters, and we know that the electric field due to 1 is going to be in that direction. It's a positive charge, so that's electric field 1. The electric field due to 2 is going to be in that direction right there, because that's a negative charge, and more or less the electric field is simply going to be equal to the electric field due to 1 plus the electric field due to 2. And we immediately know that the direction for that is going to be in that direction right there. So the electric field due to 1 is simply going to be equal to K times Q1 divided by the distance to 1 squared, which is going to be 0.2 meters. So that's going to be 9 times 10 to the 9th. And I'm going to make this a magnitude because I already know the direction is in the positive x direction. So that's going to be 2 times 10 to the -9th coulombs, and the distance is going to be 0.2 meters, quantity squared, and that tells me that my electric field due to 1 is going to be 449.4 with a unit of newtons per coulomb. Similarly, the electric field due to 2 is going to be K, and then now the magnitude of Q2 divided by the distance to 2 squared. Distance to 2 squared is going to be 0.6 meters. So again, K 9 times 10 to the 9th. Magnitude of Q2 is going to be magnitude of -5 times 10 to the -9th coulombs. Distance 0.6 meters, quantity squared. And that's going to work out to be 124.8 newtons per coulomb, and so my net electric field is going to be the sum of those two, or 574.2 newtons per coulomb, and it's going to be in the positive x direction. Just to take a quick look at point number 2, if I pick my point way out here, then my electric field due to 2 is going to point in that direction, and my electric field due to 1 is still going to point in that direction. And similarly over here, looking at negative 2 meters, so this point way out here, the electric field due to 1 is going to be in that direction, and the electric field due to 2 is going to point towards the negative charge. Now to go ahead and look at part B and find the forces. We know that the force is going to be equal to the charge multiplied by the electric field, and it tells me that it's an electron, so that tells me that the charge is going to be 1.602 times 10 to the negative 19. It's going to be coulombs. Electric field is going to be 574.2 newtons per coulomb. So you can see how the units are going to work out to be newtons. And at the end of the day, I'm going to get 9.2 times 10 to the negative 17 newtons. And that's going to be in the negative x direction. The reason for that is because this charge here is actually negative. Forgot that guy. Okay, problem 97 would be very useful when you solve 99 on your own in class. It's got a quarter circle, and it's got some negative charge q on it. It has some radius a. I'll put my little negative charge q right there. We're asked for the electric field at the origin, so kind of that's what we're looking for. Well, what we can do is we can pick tiny little segment right here, say that it's got some tiny little amount of charge on that, and that's going to cause some tiny little electric field dE. We know that it's going to be towards it because it's a negative charge, and really we're going to have its components dE x and dE y right there. And what we can really say is this little tiny dE is going to be equal to k multiplied by dq divided by the radius squared. The radius is just a, so it's going to be a squared. And what we want to do is we want to essentially integrate this guy up to get the total electric field. Can also say that this is going to be at some angle theta, and it makes sense to get q in terms of theta, so that way I can integrate from 0 to pi over 2. How do we go about doing that? Well, first we're going to say that there's going to be a linear charge density. It's going to be equal to the charge divided by the quarter circle, so 1/2 pi a. One thing to keep in mind is rather than have negative signs running around and have a negative sign right here, I'm just going to remember the direction of the electric field and just leave that guy to be positive. We can say that the charge is going to be related to the linear charge density multiplied by some tiny little amount ds that it's going to subtend, just like that. And we also know that it's going to subtend some tiny little angle. We can call that d theta right there. And we know that, I always remember standing room only, s arc length is equal to radius multiplied by angle, or ds is going to be equal to the radius multiplied by d theta. So this is going to be lambda a d theta. Now we can substitute our lambda in and say that's going to be equal to q divided by 1/2 pi multiplied by a d theta. Do a little bit of simplification, and we're going to come out with dq is equal to 2 multiplied by q divided by pi d theta. And so finally I can go back to this expression right there and say that this tiny little amount dE is going to be equal to k times 2q divided by pi d theta, and don't forget my a squared. Now I can also say, well, I know that dE in the x direction is simply going to be equal to dE multiplied by cosine theta. And what I want to do is I want to go ahead and integrate this guy from 0 to pi over 2. So I'm going to do my integral right there. Turns out we can pull all of these terms out except for the d theta. And so what we're left with is 2kq divided by pi a squared integral of cosine theta d theta. And again, we're integrating from 0 to pi over 2. We know that the integral is going to simply be a sine, so we're left with 2kq divided by pi a squared multiplied by sine theta evaluated at 0 and pi over 2. It's very easy to evaluate sine theta at pi over 2 and 0, so now we finally have Ex, which is going to be equal to 2 multiplied by k multiplied by q divided by pi a squared. Sine of pi over 2 is 1, and sine of 0 is 0, so we have the x component expression. Similarly, we're going to do the y component. That's going to be equal, or dEy, that's going to be equal to dE multiplied by, in this case, it's going to be sine theta. We want to get e of y, so we're going to integrate from 0 to pi over 2. Same as before, we can pull out the 2, the k, the q, and the pi a squared, and we're simply integrating sine theta d theta from 0 to pi over 2. We all know that's going to be equal to negative cosine theta, so 2k q divided by pi a squared negative cosine theta, and we're going to evaluate it at 0 and pi over 2 as well. So lastly, we can write e of y is going to be equal to cosine of pi over 2 is going to be 0, and then we're going to minus 2k q divided by pi a squared. Cosine of 0 is 1, so we have a negative 1 right there. The negatives are going to cancel out. We're going to end up with a positive 2kq divided by pi a squared. Symmetry would tell you that you would expect Ex and Ey to be the same, and they are. Lastly, 2199, we have two wires that are meeting at right angles, and we're asked to solve for the electric field at point P there. So we're kind of looking for the net electric field. Just kind of in our mind's eye, we can see that the top wire right there is going to give us an E1. This wire right here is going to give us an E2, and it's negative, so it's going to point towards it. And what we can do is we can recall example 21.10, where that tells us if we had a wire kind of as such going from negative A to A, and we are looking at some distance x along its center, we were given what the electric field is. Here we have the same thing. Here we're going to have our distance x, that's going to be 0.6 meters, and going from negative A to A tells us that A is going to be half that, or A is going to be 0.6 meters, and we can essentially flat out use the results, which said that the electric field for 1 is going to be equal to kq divided by x square root of x squared plus a squared, or 9 times 10 to the 9th multiplied by the charge, 2.5 times 10 to the minus 6 coulombs, distance x 0.6 meters, square root of 0.6 squared plus 0.6 squared is going to give me 44,194 newtons per coulomb, and the direction is in the downward direction, so the let's just say the negative j hat direction. Take a look and we can see, well, E2 is going to have the same exact same exact value for charge, just it's a negative, and I've already drawn the direction of it. So E2 is going to be 44,194 newtons per coulomb, and this is going to be in the negative I hat direction. And simply the net is going to be the square root of E1 squared, so 44,194 quantity squared plus 44,194 quantity squared, that's E2. Take the square root, and we're going to end up with the net electric field to be equal to 6.25 times 10 to the 4th newtons per coulomb. The direction, we know that they're equal, so that tells us that it's going to be essentially a 45-degree angle. It's going to go right there, so the direction 45 degrees off of the negative x direction, or off of the negative x plane.